Recently, I've become fascinated by this deceptively simple toy, the Tippy Top. The neat thing about the Tippy Top, as shown in this video from grandillusions.com, is that if you get the top spinning fast enough, it will flip over and spin on its stem. Instead of a narrow point at the bottom like a regular top, the Tippy Top is roughly mushroom shaped, which means the point of contact between the top and the surface on which it's sitting can be significantly offset from the primary rotating axis. As a consequence of this offset, friction at the point of contact can exert a non-negligible torque on the top, and it's this frictional torque which is the key to the top's counterintuitive behavior. But how exactly does that work? Here's our tippy top. As the top spins, the point of contact drags against the surface and experiences friction in the opposite direction as the spin. The vector r points from the center of mass to the point of contact, and the cross product of r with F gives the frictional torque. The torque has two components. One points along the primary axis. That tends to reduce the spin along the axis. The second component points perpendicular to the primary spin axis, and it's this component which flips the top over. The upshot of this is that the more friction the tippy top sees, the stronger the frictional torque and the faster the top should flip. So if we spin the top on a rougher surface, it should flip faster than if we spin it on a smoother surface. Let's see if that actually happens. So here I am spinning the top on my smooth hardwood floors. Turns out that the hardest part of this experiment was keeping the top from skittering out of frame. So to keep it in frame, I spun the top slowly enough that it didn't always invert. Doesn't change the basic idea. The smooth floor should mean the frictional torque is relatively small, and so the reorientation rate should be relatively slow. I also didn't have a lot of control over how exactly I spun the top each time, so I videoed myself spinning the top a lot and tried to estimate the time until the top's stem struck the ground. For these smooth hardwood floors, I estimated an inversion time of about 1.2 seconds. Next, I spun the top on the roughest flat surface I could find, my cement stoop. Exactly how much rougher the cement is than the wood isn't really important, I'm just looking for something rougher. Sure enough, from the videoed trials, I estimated an inversion time of about 0.6 seconds for the cement stoop, half the inversion time for the wood floors. So more friction really does make the top flip more quickly. One of the things that got me interested in this problem was this wonderful video from Veritasium that looks at the dynamics of a spinning asymmetric disk, which also flips in a counterintuitive way. I think Veritasium gets the answer right. The reason that the asymmetric disk flips over is because of the frictional torque, the same as for the tippy top. But there's some confusion in the video because the disk exhibits more complicated behavior than the top. I think that's because the disk isn't spherical, it can bounce when it strikes the surface in the right way. The video here also shows the disk spinning on ice, where friction of course is small, and therefore the inversion time is quite long. The tippy top as a toy seems to have a fairly recent history, with some websites claiming it first appeared in the 50s. It's even reported to have fascinated the likes of Nobel Prize winners Wolfgang Pauli and Niels Bohr. However, dynamical analyses of the motion of funny-shaped spinning objects goes back to at least the mid-19th century, when none other than Lord Kelvin, then an undergraduate in Cambridge, spent his time spinning oblong stones instead of studying for the great Cambridge math tripos examination.